Okay, welcome to week 3 discussions. We're asked to look at problem 60. In problem 60, we're given a graph of current versus time. Current versus time. This is in the book. It looks pretty much like this. I didn't draw the grid. So what we can do, the easiest way to find, we're asked to find the charge, right? So we're going to use our definition for current to do so. So we can take time to the left side times the current is going to equal our charge. Right? So let's just start this up. So what I did was I separated this into different sections, which would be easy to sum up. So this area under the curve is actually a nice flat rectangle. So we're going to have 5 seconds minus 0 seconds, right? 5 to 0, and then we have 0 to 2 current. That's going to equal 10 coulombs. Let's see what I have here. This is amps. Okay, next one. So this is what we'll call 1, and then the next part we're going to go to the rectangle in the middle, another nice flat rectangle. So we're going to go from 4 seconds to 3 seconds, and then we're going to go from 6 amps to 2 amps. That's going to be 4 times 1 is 4 coulombs. Okay, next one, we'll look at one of these triangles. So let's look at the left. So 3 minus 2 seconds, we'll write that down in just a moment. So 3 minus 2 seconds, and then we have 6 minus 2 amps again, but here we don't have a full rectangle, so we can't just multiply those together. We actually have a right triangle, and we can just take a factor of a half to get this area, because you could see if we had a full rectangle, it would be half on the other side, right? So we have half of this rectangle here. We have 1/2 of 3 minus 2 seconds times 6 minus 2 amps. That's going to equal, what do we have? 4 times a half, so 2 coulombs. And then pretty much we have 5 minus 4 is another 1 second, right? And then 6 minus 2 is another 4 amps. So it's pretty much exactly the same on the other side. So we'll take 5 minus 4. It's going to give you 2 coulombs. So that gives you a total of 18 coulombs underneath the curve. Okay. Great. Okay, next. Part B asked us to find what constant current would transport the same total charge during the 5-second interval as does the actual current. So what does that mean? It's asking us to find a current. Total charge is 18. Right, so if we recall the formula, right, total charge over change in time, we have 18 coulombs over 5 seconds is going to give us a value of approximately 3.6 amps. So that is what the current would be if it were constant, right? Okay, next problem. 1755. Actually have it written down here. So we have we're given that we have a wire with a specific resistivity, 3 times 10 to the negative 8 ohm meters. It has a cross-sectional area of 4 times 10 to the negative 6 meters squared. We apply a 20-volt battery to it, and we expect it's going to develop 48 watts of power. So what is the length of wire required for this scenario? So we actually have a couple of relationships that we can use. We have, if we look in the summary in the back of the chapter, we have resistivity times the length over the cross-sectional area. And we can also use power is equal to delta V squared over the resistance. This one is number 17.9 in the book as well. I don't know what let's look. The first one that I used is 17.5. So this is 17.5. Okay. So applying these, so what are we given? The reason I chose to use these is because we are given a potential difference, right? We're given 20 volts, so we can apply that. We're given a power, so we can apply that. We don't know the resistance, right? So I can solve for resistance and set these equal to each other. We know the resistivity, we know the cross-sectional area. So we can use all of this to find the length. That's why I'm using these two particular formulas. Okay, so we have resistance is equal to resistivity times length over cross-sectional area is also equal to, using this formula here, is also equal to delta V squared over the power. So now that we have this set up, we can solve for length, which is the thing we're asked to find. So length is going to be equal to delta V squared over the power times area times 1 over the resistivity. Right? And so if we plug all of this in, if we plug the values we're given in, 48 watts times the cross-sectional area was 4 times 10 to the negative 6 meters squared. Right, and then we also have, what was it? The resistivity is 3 times 10 to the negative 8 ohm meters. This is going to give us a value of 1,111.111 meters, or approximately 1.1 kilometers. That's the length of the wire, which is pretty long, actually. Just double checking the units real quick. We've got area, meters squared, times volts squared, which is our delta V, over watts, right? We have watts, and which is also a joule per second. We also have over ohm meters, right? So this is going to be, get rid of that and that. So now we have, well, we can translate this to amps over volts. Volts squared, seconds, because we had joules seconds, right? And then we had, so that gets rid of that and that. So now we have meters times amps times volts over this. Joules per second is still a watt, because now we can translate our volt into watts per ampere. And that's going to cancel, 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 and that gives us units of meters, which is what we wanted. So that's good.